Hello.
Hello.
Hey, Barry, how are you? And I see also of Mark.
Yeah, this is Mark.
Okay, hi, Mark. Let's give it 2 or so more minutes. Let's see if anybody else is going to hop onto the call.
Very good.
Okay. Okay, so I've emailed out, I've posted to the announcements section of Blackboard a spreadsheet that I'm going to be using for discussion today. So if you want to open that up and follow along, please go ahead and do so. All right, so let's go ahead and get started here. And I'm going to quickly share my screen. And so chapter 3 looks at, again, we're still in that descriptive stage of reviewing statistics. So we're still trying to make sense of data. Once we've received a database or a set of data, and you want to get a basic understanding of what are the characteristics of the data. And so in chapter 3, we look at some of the basic ways that we can actually describe this nature of the data that we are presented with, okay? So in this chapter, there are a couple of things that you're expected to be familiar with. One is what is the mean, what's the median, what's the mode, how do you go about calculating and interpreting these? And then we take it a step further and look at what's called a weighted mean, and we also look at a geometric mean, okay? And all those are called measures of location, basically trying to tell us how central our data is around a given, some given value, okay? After that, we're going to look at measures of dispersion, okay? And I'll explain that when we get to the discussion of range, variance, standard deviation. And then we look at very briefly at Chebyshev's theorem, as well as the normal curve, and how does that impact our analysis, okay? So before I go into this, I just wanted to ask you guys, do you have any questions about the homework assignment? I'll be posting the solutions with a brief discussion, video discussion to Blackboard later today. But One thing that I received 3 different emails from people asking a bit more about the Excel portion of the assignment, so how to go about doing certain things. So what I've posted to that spreadsheet that I've sent out, let me go there, is that I've decided to post whenever I use a given formula, I'm going to put the formulas to one side of the spreadsheet. So that way, if you can't remember what was the formula that I used, you'll have them listed here, okay? So that hopefully should make it easier to use formulas to try and quickly calculate whatever it is that you're being asked to calculate in Excel, okay? All right, so let's go ahead and get started. All right, so our first, the first thing that we look at is these measures of location, okay? And basically the measures of location enable us to describe data in terms of what's most frequently found in the data, because that gives us an information that we can use to make a generalized assumption about our data set, okay? A very commonly used statistic is a mean, and the mean basically tries to get the averages of a given data set, put it together and give us a value that describes the centrality of your data around a given value, okay? So this should be something that you're all familiar with from, I would even say possibly as far back as elementary school or middle school or high school. But let's go ahead and go through the mean, the median, and mode, and how to go about doing that in Excel. Okay, so the first tab that I have at the bottom here has to do with the population mean. Okay, in statistics, we're going to be looking at both population and sample. It's if you're lucky enough to have all the data sets for a given problem, then you have a population-based problem. And that is good because you're not going to be making assumptions or trying to make some inference about the general population because you have all the information available to you, okay? So if you look at your textbook, we have this question here that talks about the fact that there are 42 exits on I-75 through the state of Kentucky. Listed below are the distances between the different exits in miles, okay? And the first question we have here is, why is this information a population and not a sample? Okay, so it's a population basically by virtue of the fact that it has all 42 data points, which are the number of exits within the state of Kentucky. So it's a complete sum of all the exits. So we're not making an inference about a population. We actually have the population. We have every single observation or every single parameter that needed to be able to make a full analysis of this data, okay? If we only chose 5 or 10 exits and we're trying to make an inference about those exits, then we have a sample. And when we'll be doing our measures of dispersion, you'll see that there's a small difference in how we go about calculating your variance and your standard deviations, okay? So starting off with the mean, in Excel, is the same data set that I have here. The mean is simply, we use the average function, okay? So basically the mean, let me bring out my pencil here. The mean is calculated by adding up all the data sets that you, data points that you have all the way to some value n and dividing it by your total number of observations, okay? In Excel, this is done through a very simple calculation using the average function. And so rather than adding everything up using 11 plus 4 plus 10, you just use the average function. So that should be pretty straightforward. And we'll go ahead and do that here. And so using the average formula, I'll just highlight all my data and we get our mean value, okay? So this tells me that on average, there's approximately 4.5 miles between the exits in the state of Kentucky. Okay, so that's a measure, measure of location. It's the most commonly used measure of location in statistics because it's very easy to understand, it's very easy to calculate, and it gives us a sense of the magnitude of whatever it is that we're looking at, the average magnitude of whatever parameters we're looking at. Okay, so in this case here, our mean is 4.57 miles, and that satisfies that requirement. Very simple, very easy to do. The thing to remember is that you're just taking the sum total of all the observations, dividing by the number of observations. Okay. A longer way of doing that would have been to do a sum where I would add everything up here, just highlight everything and hit enter, and then I would divide this sum by the number of observations, which was, I believe, 42. And we'll get this exact same amount. Okay. So that's our first measure of location. It's very basic. It's very easy to understand, and that differs from our sample mean. Okay. Now, when you'll be looking at data throughout the textbook, you'll see certain variables have a capital letter, certain variables have a small letter. So the capital letters represent data associated with the population. Small letters will always represent data associated with a sample. Okay, so just make sure you keep that in mind. Capital letters, that's a population-based data. If we have small letters like you see a small x or a small y, chances are that you're looking at a sample. Okay. So a question that I got was that difference between the arithmetic mean and the population mean. The way you calculate it is pretty similar. It's just that the arithmetic mean is how we usually look at the sample mean. Okay. So again, here there's really no difference apart from the fact that when I calculate my value of 97.5 here, that average will not exactly equal the population mean. So what does that mean? In this case, the question was, Verizon is studying the number of minutes used by clients in a particular cell phone rate plan. So they collect a random sample of 12 clients, and this is the number of minutes shown from that sample. Okay. Now, this 97.5 might be representative of the population, or it might not be representative. So there's the possibility that this is not a representative sample, depending on how these guys went and collected that data. Okay. It could be that they collected this data in a college environment where students are online 24/7. Or it could be that they went to a nursing home and collected this at a nursing home where the people use cell phones at a much lower rate. Okay, so the manner in which you collect your data, your sample data, is very important because you want to make it as representative as possible of your population. Okay, so we have ways to try and figure out first of all, whether this arithmetic mean closely equals the population mean. Okay, and one of the things that this will come up later when you're looking at sampling is we'll consider the sample size. Okay. So the larger the sample size, the greater the possibility that your sample's mean approximates the population mean. But at the same time, there's a cost associated with getting a large sample size. If I wanted to go and observe 10,000 people, chances are that I'll have to either incur slightly more cost or take slightly more time. So there's that trade-off that has to be made, but there should be a minimum sample size that would be representative of a given population. Okay. So we're not yet there yet. For now, just know that there's the sample mean is an estimate of that population mean. Whether or not it's accurate, that's yet to be determined. We've not yet gotten there just yet. Okay. So the other measure of location is the median. And the median is basically what's that centermost number within our data set. Okay. So if we have a data set of, say, 100, we ask ourselves, what's that data point which is at approximately the 50th observation, between 50 and 51, okay? And this involves doing one of the first step would be to first of all arrange your data in order, okay? So in this case here, we've been given an example from the textbook where the number of hours a sample of 10 adults used Facebook last month is given below. And we want to figure out what the median is. So to calculate the median, always sort your data from lowest value to highest value, okay? And since this is Excel, you really don't want to spend too much time typing data. I'll just copy this and I'm going to transpose paste this. Okay, so paste special and look for the transpose. And the reason why I want to do that is I want to have this in a column so that I can sort this from lowest value to largest value. And once transposed, I have Excel functions here. You can now sort this from smallest to largest. And then I'll take that same information again, and I'm going to paste it here and transpose it back. Okay, I have this data right here that shouldn't be there. So let me move it down. So I'll copy that again, and then paste special, transpose. Okay. So now we have our data sorted from smallest to largest. I can now try and determine what's the median value. So we have a total of how many data points here? At the bottom here, it tells me you have a total of 10. I have to figure out what's the median value. I could pretty much count from 1, 2, 3, 4, 5. So my median value should be one of these two here, or some average value of that, okay? So if you have an even number of data points, your median will be, you take these two values, divide them by 2, it gives you a number. If you have an odd number of data, then it becomes very easy to pinpoint that median value. So in Excel, we have the median formula, which when I highlight this, it's going to give us a median value. Okay, so using equal median, highlight your data, you get your median as being 6, and that 6 is the same as 5 plus 7 divided by 2. Okay, so that's again a very straightforward measure of location for your data. Okay, and it's used also pretty often. There are times when your average value is not representative of what the true figure of a given population is. Okay, so let me give this example here. If I was to take say the earnings of US citizens across the country, all working adults, and try and figure out what's the average, no, let's use net wealth. Okay, so I have a population of, say, let's not use the whole population, say the working population, say 150 million people, and I want to find the average net wealth. Okay, if you understand the US demographics, there's this thing about the top 1%. Okay, the top 1% hold a pretty significant amount of all US wealth. And if I was to get the average of 150 million Americans, that includes that 1%, you might end up with an average wealth figure that looks like, I don't know, 500,000. million than 500,000. Okay. But this might not be fully representative of what's witnessed across the United States. Why? Those guys at the very top of the wealth pyramid actually control way more wealth than most of the other people. So when you're looking at a wealth graph, it would look something like this. Oh, no, we can't do that. So let's assume, let's have an income, and then you have 10,000. Let's make this income rather than 20,000, 40, all the way to say 5 million up here. Okay, so you'd find that most Americans would be found somewhere there, but then you have very few at the end. But these people at the very end here contribute a lot to the net wealth of the country. And so when I draw my median, my average might not center upon this very place where we have our average. Okay, so the median might actually give us a better representation of what the wealth across the United States might look like, rather than having us look at just the average, because the average might throw us off if we have some outliers or some significant people or number of observations in the tail ends of the chart. Okay, so the median is another measure of location which might be useful depending on whether or not you have what's called a bell-shaped curve. And if you have a bell-shaped curve, your mean and median would pretty much be close to each other. The mean should closely equal the median. If we have a curve that's skewed to one way, then those two values, the mean and the median, stop being together. Okay, one might be greater than the other, and then the task of the statistician is to determine which one is more representative of the population. Should I use the mean and describe the mean, or should I describe the median? Okay. Now, the next measure of location that we look at is the mode. Okay, what's most common? What value is most commonly found in a given data set? Okay. And again, if we are using a given data set, mode can be found using the mode function. What's a mode? You have the mode function where you just type the word mode and then look at a given data set. And this one's going to be interesting because I see multiple modes. Okay, so it'll take the very first mode that it comes upon. So here we have 3, 3. There's a 5, 5, 9, 9. It cannot, sometimes Excel doesn't do this very well. You might actually have to find a different way to do this other than using Excel's mode function. Okay, but if we had, say, another 5 here, okay, where we definitely had a mode that was, we had one observation occurring more frequently than the rest, then that's the one that we have here. Okay, in situations where we have multiple modes, it'll pick up the very first mode that it comes across and report on that one mode, which is not really very accurate. Okay, but the mode again is just basically looking at your data to try and figure out what's most common in our data set. Okay, so if we had this is in your textbook, I'll take it out from here. So if we are looking at the ages of kids in a second grade, chances are that we might look at data that looks something like this. Second graders would be 6, 6, 6.5, 6, and that 7, 7, 7, 7.5, 7, 7.5, and so on and so forth. But when you calculate your mode, you're just basically looking at what's the most common value that the data shows. And that again becomes a measure of location that enables us to know that we have a whole bunch of data. What's most common in our data is this value of 7. Okay, if it was a second grade class, chances are that the average, most of the students in that class would be around 7 years of age. Okay, so those are the 3 basic measures of location. Sometimes those measures are not enough, and we have to make certain adjustments to those measures. And that's where we come up with a weighted mean and a geographic mean. Okay? And the weighted mean comes into play in situations where you might have different classes or different categories of a given observation. And for each given class, you have a certain frequency. Okay. So looking at this example here, this is a perfect example of a weighted mean calculation where we look at the Carter Construction Company pays its hourly employees $16.50, $19.25. There's a total of 26 hourly employees. 14 are paid at $16.50, 10 are paid at 19, and 2 are paid at 25. Okay, so those we have 3 classes or 3 categories of income of pay. And your weights here are the number of employees who fall in each pay classification. Okay, so the weighted mean basically asks you to look at. It could be, you could do it this pretty much the same way as what we have for a population mean or sample mean, where you say, okay, we have 14 people earning $16.50, and you decide you want to list these out 14 times. That 14, you need one more. And then we have 10 people making $19 an hour. So and then we finally have 2 people earning 25. Okay. So using the population mean approach or the sample approach, we would basically just do the average of all these numbers. And let's try and compare. So average here is 1820. Okay. Now let's use a simplified approach where we know we have 14 people in the first pay grade, 10 people in the second pay grade, and 2 people in the last pay grade. So rather than adding every one of these up all in the sequence that I had it here, we can use what's called a sum product function to quickly multiply this first category by its weight, the second category by its weight, and the third category by its weight, and add them all up together in one very quick step. Okay, so we have the sum product function equals sum product, and you have to tell Excel what are the different classes that you have. So this first class has a weight, the pay of $16.50 with a weight of 14. Sorry. You have to do this. You have to do this column-wise in this case here. So we're going to do the sum product, the pay, each of these 3 pays, comma, multiplied by their respective weights. Okay. And once I've done that, I can then go ahead and divide these by the total weight that we have here. So the total number of employees that we have, which was 26. So I go ahead and divide this 471 by 26. And I come up with the exact same value that we did when we did the longer approach, which was to use, to add each and every one of the data points up in sequence, like in order, and then divide that by the total number of observations. Okay, so again, arrange this into a table, and then multiply your different levels of classification by the corresponding weights, and then divide by the total number of observations, which is what you'd have in the weighted mean formula here. Okay. So what we did in this very first step corresponds to what's in the numerator here, where we're looking at the weight 1, which is 14 multiplied by our first pay level, which is 1650, plus the second weight, which is 10, multiplied by the second pay level, which is 19, and so on and so forth. And we divide all that by a total number of observations, okay, which are what we consider our total number of weights, the sum of the weights that we have, okay? And that then gives you this figure right here, this figure of $18. Okay. So your weighted mean becomes, the weighted hourly pay is $18.12. Okay. Now, moving on to, and I apologize, a lot of different things covered in chapter 3 that we're trying to cram into an hour and a half. The geometric mean is an interesting one. And the geometric mean is most often used in finance, where, let's take a simple table here. Say I'm looking at profits, and I have profits of, let's go by year, or by quarter. So say Q1, and these are, so this could be maybe 2016, and then 2017, 2018. Okay. And we'd have some values for profits in the millions, say 10, 11, 12, 15, 18, 24, 23, okay, which is typical of what you might find. Companies make profits, and you'd expect over time, if you had to graph your profit curve, companies want profits to increase from quarter to quarter. So let's insert here. Oh, what did I do? Wrong screen. All right, so let's insert line chart. And you'd expect to see something like this for profits, some upward trend to your data, okay? Now, if I was to get the average profits that this company makes using the population mean approach, I'll just use the average formula here, right? And add everything up, and I get a value of 16.9. So you'd say the company's average profits is 16.933. But is that really the case? Is that really the true representation of the data? Because if my profits are increasing over time, I might want my my calculation to capture the fact that there's some growth to the data. Okay, so the geometric mean does that. It's able to capture that growth to your data that this might not capture. Okay, so for example, if I look at the profits over the past 1 year here, the average is average of 2018 is approximately 21.75 million, which if I was to report that, our average profits are 16.93 million, that might not be as accurate as it should be. Okay, that's the average for all 8 years. That might not be the best approach to figuring that out. Okay, so we have a formula, the geometric mean formula, that captures that growth associated with the data and enables us to get a mean that captures data that's more relevant to us, which is the more near-term data than data points that are further away. Okay, and so that's what we have with the geometric mean formula here, where you have to know how many observations you have. Okay, and you're going to multiply those observations and divide them by the root of the number of observations that you have. Okay, so how do you go about doing that in Excel? And let's leave this here to compare the information we have here with our geometric mean. Okay, so we have the geomean formula, and the geomean formula would give you the geometric mean of a given data set. Okay, so you put geomean, highlight your data points, and it will automatically do the calculations for you to multiply the 10 times 11 times 12 times 15 times 15.5 all the way down to times 23, and then give us the nth root, which in this case would be, we have 12 data points, so the 12th root of that multiplication that we're going to have. Okay, and it comes up with a value that we can then go ahead and use, which is our geometric mean, right? So that's something else that's commonly used in finance. Rather than using the population mean, it's often better to use geometric mean to give you a better information on the nature of your data going over a period of time where there's some growth. All right, so those were the measures of location. Next, we move to the measures of dispersion. Okay, and the measures of dispersion just basically we're trying to figure out how far away are the different data points from some given central value. Okay, so if I was to take one of my classes, my on-campus classes, and ask the students, how old are you guys? So say this is a class that mixes both traditional undergrads and some of the degree completion program students. You'd end up with a possible survey of, if I take a sample of 10 students, it would be say 18, 19, 18, 21, 20, could be an older student in the classroom. How many points? Maybe 21, maybe another older student, maybe a really young student. So you end up with some data points here, okay? And we might be interested in finding the mean of this data and basically figuring out how dispersed our data, different observations from this mean value. Okay, so here we could have a situation where we're looking at what's the difference between this value and the mean. Okay, so the first value is way below the mean, and then you'll end up with data points above and below the mean. Okay, now the measures of dispersion basically try and enable us to determine how wide is that variation. Okay, and I could compare this dispersion with a different dispersion where, for example, let me compare two. I have a second class, and this second class, the average age of students is calculated as, okay. And when I look at this here, these values that I see here, if I was to add these up and compare them with these values here, okay, I should have squared those values. Okay, you'd find that if you compare two values, two different data sets, one data set might have a wider dispersion in terms of, in this case here, we have people who are 40 years old, we have people who are 35. So we have data points which are further away from the mean than this one here, where we have a whole bunch of people who are close to that mean of 21. Okay, and I was hoping I could capture that by, yeah, that won't be Let me delete that. Okay. So the measures of dispersion basically try and capture how far are we from that mean value, from the median. Okay. And the first and simplest measure of dispersion is your range, which basically asks you to calculate the difference between the largest value and the smallest value in your data set. Okay. So the range requires that you calculate what's the smallest and what's the largest value. If you have a data set this small, you can visually look to see, okay, I have 10 data points or 9 data points, and the smallest value I have is 17. Largest value I have is 40, okay? Now, that's not practical, and if you're working corporate, chances are you're dealing with data that's a couple of, if you're to print it out, it'll be a couple of pages long. Might have 50,000 rows of data that you're dealing with, so this is not very practical. Okay, so in Excel, to get rid of that in practicality, we can use the min. Let me put this here. I forgot to add this here. Excel functions. You can use the min function and the max function, and just put equal min. So this will give you the minimum. Highlight that whole column, and for the maximum value, you put max. Highlight the whole column again, and you get the same information as what I got just by visually observing the data. Okay, so with that, now we can calculate how large the range is by subtracting. So your range is basically your maximum value minus your minimum value, which would be 40 minus 17. And so we have a range of 23. Okay, so that tells us how widely dispersed the largest data point is from the smallest. Okay, it's good to know, but sometimes this range might be really misleading. So for example, if I had a data point which instead of being within that range, I had one outlier, which was 1,200, or yeah, say 1,200, then my range tells me that our data has a really wide dispersion when in essence, it's just the one point that's throwing everything off, okay? So the range in and of itself is not a good measure of dispersion. We need to have other measures of dispersion that can take into consideration this outliers, the presence of outliers, okay? So that's where we come up with the population variance, the sample variance, the sample and population standard deviations to try and better understand how widely dispersed our data is around that mean value, okay? So let's go to the population variance tab, and it's blank. We need to get a data set. Let's see if we have some on the PowerPoint that I posted out there. Boom, 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 boom. Okay, I thought I had information on this, but I guess I don't. All right, so let's build a sample based off of the information we have here. So hourly wages, 12/20/16. Actually, I do have it here. And we can use it here. Okay. Now, the population variance requires you to calculate, first of all, what's the mean associated with your data. And then you have to calculate for every value that you have here. Actually, let's do it step by step. So first calculate your mean, which is calculated by the average value of what you have here. Okay. And with this figure of 17, we can now calculate the difference between the hourly wages and the mean wage. Okay. And that is usually put down as X minus X bar. X bar is just another way of saying the mean. If I was able to draw X bar is just basically how you'd go about having something that looks like X bar. And since I don't have the time to do that, I'm just going to write X bar. Okay, so I'm going to calculate the difference between every data point and the mean minus your mean value here. And because I want to drag the formula down and have it, if I drag this formula down, this is what's going to end up happening. It will give me figures which are not accurate. And the reason why they're not accurate is because it's referencing the wrong cell. This is referencing a cell which doesn't have data. So I want to always reference this cell in blue. And how you go about doing that is to highlight your cell B7 and hit your F4 button on your keyboard. And that way now, if I drag this formula down, I'm able to get the actual difference between that observation and the mean. Okay. And if you see here, it references the two cells that I'm interested in. Okay. Now, after calculating the X bar, I want to get rid of those negatives, and how I'd go about doing that is to calculate the square of your X bar raised to, actually, let me just put a 2 here. And I'm going to raise that. Okay. So this step here involves multiplying that by itself. And we come up with those values that I want to now add up. Okay, so we come up with our x minus X bar squared. If we add them up, we come up with this figure of 40. And if you look at the formula for your variance, which if you go back to the formula that you have in your textbook is given by you summing up those differences, squaring them, and then dividing them by the number of data point or observations in your population. Okay, so in this case here, assuming that this is our population has a count of 5. To calculate my population variance, I'll divide this value here by 5, and I get my figure for variance. Okay, so the variance is just basically a measure of dispersion that tells us how far are the different data points away from that mean value. Okay, now variance kind of explodes that difference between dispersion between the different points and the mean. And usually if you have really big figures of variance, so say for example, if we had a CEO here who was making say $150 an hour, your variance is exploded. So that tells you that there's a really big discrepancy, there's a big difference. And if I combine the range here, I see a pretty big range, and that huge variance there, that tells me that there's certain data points in our data which are really far dispersed from that mean value. Okay. Variance does not fully show the average size of dispersion. To get the average size of your dispersion, this is your variance. You need something called the standard deviation. And your standard deviation is basically the square root of your variance. Okay. And the square root formula is in Excel, it's SQRT. And just click on that variance, and I come up with a number. Get rid of all those zeros. So now I have my variance and my standard deviation. This standard deviation for me as a researcher I find it more important for my research purposes, because this tells me the true average size of the difference between the mean and those different data points. Okay, So it's basically telling me for the first observation that I have a difference of $5. Second one I have 3, third one I have 1, 1, 2. So on average, the average of these here should be around 2.83, okay? So some values are above the mean, some are below, but the average deviation is approximately $2.83, okay? So that's your variance and standard deviation. Another way of doing this, which is the fastest way in Excel, would be for the variance to just use a variance formula. Okay. When you're using the variance formula, you have to ask yourself, is this a population or is it a sample? Because there are two calculations for variance. There's the variance of the population, which is var.p, and below that you'll have a var.s, which is the variance of the sample. Okay. So the variance of the population dot p, if I highlight all these numbers here, I get a number, and that number is 8, which is similar to what we had here. Okay. So Excel has this fancy ways of calculating stuff for you, rather than doing it the long way, which might be what you asked for in the homework assignment. I'm trying to remember, maybe not. But you can use Excel to calculate the variance, and then once you calculated the variance, you can also calculate your standard STDEV.P, the standard deviation of your population, okay? And you'll get the exact same number that you get by using the square root of the variance, okay? So those are two ways of calculating both the population variance and the population standard deviation, okay? The thing to remember here is that your standard deviation is the square root of the variance, of your calculation of variance, okay? So that's your population, and obviously this, I took the sample information and used it in the population. So this is assuming that we have 5 employees as employed in a company, that's everybody, then that can be considered a population. If we don't have the entire population and these 5 people is just a subsection of the employees, then we calculate variance and sample standard deviation slightly differently, okay? Remember, I talked about the fact that if you're using a sample, there's a chance that your sample might not exactly equal your population, okay? If I have 5 employees and we're General Motors, we have 10,000. We have 10,000 employees working for us. Chances are that these 5 employees, the average, the sample mean, the sample variance might not exactly equal the population's variance and standard deviation. So then we have to adjust, make an adjustment to factor in the sample size, and also the fact that this sample is not a true 100% representative of the population. Okay, so how we go about doing that, the main difference that we add to our formula is we're going to have an n minus, instead of having n, we have an n minus 1. Okay, these two formulas are pretty much the same. The thing that I remember I told you is that if you see a capital letter, you're dealing with population. Capital N, population, number of observations. Small n is the number of observations in the sample. The other thing that I forgot to mention, your population will always use capital letters, but you'll also use Greek notation. Okay, so you'll have sigma, alpha, beta. That usually refers to the population characteristics. If it uses smaller capital letters like the small s, we're looking at a sample. So just keep that in mind. If you see a Greek notation somewhere, just remember you're dealing with the population. Okay, so let's use the exact same information we have here. I want us to compare what our results would look like with the sample. Actually, already have it here. Okay, and the first step is to calculate that sample mean, which is an arithmetic mean using the average formula. What did I do wrong? B2 to B6. Okay, so this sample mean in this case here converges with the population mean because I'm using the exact same data set. And so I expect that when I'll be calculating the variance, there might be some similarities, but let's see if we actually do have a similarity. So to calculate the variance, I'm going to get this x minus x bar squared. This actually should have been the sum. So this will be this divided by the number of observations, which in our case was 5. 1, 2, 3, 4, 5. 5 minus 1. Okay. And then our standard deviation for the sample would be the square root of this value here. Okay. So we come up with two numbers. Our sample variance is 10, standard deviation is 3.16. And let's compare it to what we have here. Here our variance was 8 and the standard deviation is smaller. Okay. So that addition of the n minus 1 is just for us to ensure that there could be a level of error in your sample. We're going to add just a little bit more leeway by adding that samples or whatever value we get for our sample variance or sample standard deviation is going to encompass slightly more data because we might be off by a certain amount. So the n minus 1 enables us to capture the fact that there could be error in the data that we have. Okay, so that is your sample variance, and you could calculate it too the same way if you use Excel functionality. So here we have variance of the sample, and you highlight all your samples, and then you get your standard deviation for the sample, which is standard dev.s, where the S stands for your sample. And again, you get the exact same data as you had using the longer approach. Any questions before I continue? Should have asked this sooner. But if you have questions, you can always email me about anything you didn't understand. Okay. So again, these are measures of dispersion, how far the different data points, the observations from that sample. Okay, and as I said, the thing to remember here is that your standard deviation is a pretty accurate measure of how wide the dispersion is between the different data points and your measure of dispersion and your mean. Okay. So let's see how we're doing on time. Disappeared. Okay, so let's continue for another 5 or 10 minutes and let's just finish up what's called the Chebyshev's theorem. Now, we've talked about standard deviations and the fact that most data points don't usually lie exactly on the mean. So there's some measure of dispersion. This gentleman called Chebyshev came up with this theorem where he said that it's possible that if we have a certain number of observations, say, let's just have very basic, 5, 6, or 10. Okay, so we come up with a number of observations here. How many are these? So we have 18 data points, 18 observations. First thing that I would be interested in is what is the mean? And your mean is your average of your data, right? And we have here we come up with an average value of 6.11. Okay. Now, I might be interested in knowing for a given data set, how much of my data lies within a certain number of standard deviations from the mean. Okay, how many lie above? How many data points lie maybe one standard deviation above the mean or two standard deviations above the mean? And so the first thing that I need to ask myself is, how many standard deviations am I looking to go above this, above or below this? So it could be 1, or it could be, the most commonly used standard deviations are either 1, 2, or 3 standard deviations above the mean, or above or below the mean. So K is that figure that we're trying to figure out exactly how many data points lie within some standard deviation units above or below the mean. Okay, so Chebyshev says that with this formula that he came up with, you can actually determine for a given data set how much of this data is going to fall within, say, 3 standard deviations from the mean. Okay, so to calculate, say, let's start with 3 standard deviations above or below the mean value of 6.11. And he says that we use this formula, which is a 1 minus 1 divided by K, which is how many standard deviations. Okay, and that K has to be raised to the second power. So you get the square of K, and you come up with a number. Okay, now let me explain this number, because this might be a bit confusing. 0.88, let's make it a percentage just so that I can explain it better. So 0.89, according to Chebyshev's theorem, tells me that 89% of all the data points that we have here are going to fall within 3 standard deviations above or below the mean. Okay, and usually, when we'll be discussing the normal distribution, this will make more sense. But let me try and explain it here. So assume that we have what's called a normal curve, which you guys have not yet covered yet, but is something we'll cover in maybe 3 or so weeks. We have our mean right here, and our mean here was 6.11. Okay. When talking about standard deviations, we're just basically saying we have data points. There's one data point that is 5. I'm going to look at the list I have here. 5. There's a 6 somewhere there. There's a 4. There's an 8 somewhere there. 5, 7, the 9. So we have data points scattered all around. That's how most data would be. When we talk of standard deviations, we have one standard deviation from that mean value. So this is our mean value x bar. This is one standard deviation below, one standard deviation above, 2 standard deviations. So this is 2 below, 1 below, and then we have 3 standard deviations above and below our mean. Okay, let me use a different color for this mean. So we're basically looking at how dispersed are this information. And according to Chebyshev's theorem, at 3 standard deviations, we're going to account for 89% of all the data points. So if we have 18 data points, according to Chebyshev, we're going to have 18 times 0.89. So around 16 of those observations that we have here should be included within 3 standard deviations above or below. So there might just be one point above, 1 point below, something like that. But most of the data points should be within 3 standard deviations. Okay, if we did a 4 standard deviation, then 94% of all the data would be included within within 4 standard deviations plus or minus, and you can go up higher all the way to 6 sigma. Usually encompasses most everything that you're going to have in your data set. Okay, so it's a very simplistic way of trying to determine very quickly how much of our data will be within 1 standard deviation, for example. Okay, and in this case, it's telling us based on the nature of our data. Let me see if I have this correct. Let's move it to 1.1. Wrong place, and do make this more visible. Okay, so 1 standard deviation from the mean, we expect to have maybe 17% of the data that we have here. Okay, the thing to remember is that your value of k has to be always greater than 1. Okay, or if it isn't, then you end up with the same problem that I ran into, where your data there your solution doesn't make sense. Okay, so that's a very quick way of doing what we'll be doing when we look at normal curves. And basically, when we look at normal curves, drawing, which is the very last thing that I'm going to talk about right now, is the empirical rule. Okay, so Chebyshev's formula piggybacks off of what is our commonly accepted empirical rule of data. And we usually say that if your data has this pattern where you have a bell shape to it, where the vast majority of data points are close to that mean value, and then we have fewer and fewer data points going away from the mean, 68% of your data will fall within plus or minus 1 standard deviations. 95% of your data will be within 2 standard deviations, and then almost everything will be within plus or minus 3 standard deviations from the mean. Okay, and this is something that we'll go into in greater depth, I believe, next week. Not next week, but after chapter 4, when we go and look at distributions, we'll look at the normal distribution, and this will make a lot more sense. Okay. All right. I want to end right there and ask if there are any questions. Let me see if there's anything I didn't cover for the chapter. So that should be sufficient to get you going with your as you read the textbook on your own at home. And if there's anything I missed, I'll just post an additional video to Blackboard. Okay. So if we don't have any questions, let's call it a day. It's a lot of information, but hopefully it helps you get through the chapter better. And what I'm going to do is repost this to Blackboard. Actually, let me use the very same one. And attach this more complete version of the spreadsheet. All right. So go through the chapter, see if you can get through the different questions associated with the chapter. And if you have questions, shoot me an email. But that should be it for now.
Thank you.
Okay. All right. You'll have a good evening.
Likewise.
Okay.